All right, and now for lecture 11.3, multivariate correlation structure in multivariate miscellany in our module on multivariate models. So the optional readings for class today are a few really nice and helpful. The first is a website with code related to a macroevolution workshop from 2017 that I was inspired by and got data from, so that was super helpful, and it has a lot more examples for a lot of different types of things if that's of interest to you, and I would recommend it. And then I just want to recommend the classic Mixed Effects Models in S&S Plus book and the unit on correlation because it was really helpful. This book is really great, and if you're doing mixed effects models in any sort of serious way, you should probably look at this. Okay, so sometimes when running linear models and generalized linear models, you want to account for a correlation structure that is more complicated than simple autocorrelation in one dimension, like we've talked about, so in space or time. So you may want to include an entire correlation matrix or distance matrix. In essence, you are using this matrix as a random effect of sorts. So for example, you may want to control for the phylogenetic relationship of all of your species or individuals to each other. And these models tend to be a lot more custom build, and they deviate quickly from the basic ways to structure your correlation arguments in LME that we've talked about in the past, and how we did this with spatial and temporal autocorrelation, but we're going to go over some basic examples. So I want to not jump in too quickly and take you back to our autocorrelation reminder. So looking back at our mystery snail example, we remember that there were 6 measurements of biomass consumption through time by snails per individual, and we decided that it may be more likely that measurements closer in time are more likely to be more similar to each other than those farther in time. And so we ran a mixed effects model with an LME where biomass is a function of sex and month because that's what we were curious about, and a random effect was individual. But because we believe there could be some sort of correlation in time, we used ARMA model or AR1 model with a correlation AR1 and used month as our time there, and things could be correlated. And we did see that there was a correlation here in time. Okay, but let's try to think about beyond just a single space or time. What if you have a matrix of correlation? And we're going to be looking at data on closely related barbet species. So we'll be looking at an example of Asian barbets. They're super cool birds that disperse a lot of seeds. They're frugivores. They disperse a lot of seeds. And this data set was used in the macroevolution workshop that I mentioned. And the scientists working with this data were interested in understanding the factors associated with the evolution of song in these birds. And so here is what the data look like. And I will mention, to make this work, I had to make sure that the first column wasn't actually a column, but instead was names. And so I had to use the old-fashioned read.csv with a special argument to make sure that that first column became the row names and not a column. So I would recommend checking out that code if you do any of this. If you want to get this to run, you have to make that first column not actually be a column. So in this case, wing is the first column. And so why we need to be thinking about a correlation matrix here is that we need to take into account the possible correlations among traits in closely related species. So some of these species are going to be more closely related than others. You can see the tree here that represents all of the species of barbets that we're looking at. And species that are closer are more likely potentially to have similar traits than those that are far away. And so we want to make sure that we're accounting for that in our model. And so one thing that you really need to make sure you're doing when you're working with this data is you need to make sure that you have the same species and spellings across your tree and your data set, right? So you need to make sure you have a tree and a data set. That's how this works, because your tree is what you build your matrix from. And you can use this name.check function to check these things out. And so when we do this, we see that there are 9 columns in the tree that aren't in the data, and there are none in the data that aren't in the tree. So we have these 9 species, and we need to drop them using drop.tip, and that helps. And this is for using the specific kind of tree that's specified here, but this, there's lots of ways you could make these trees. Okay, so once you have your tree where you've removed the tips that you don't have data for, we can start creating our correlation matrix. And so what we're going to be doing is this phylogenetic least squares model is equivalent to a linear model with the correlation structure that matches the phylogeny, assuming Brownian motion. So first we have to create the correlation matrix, and we use this function core Brownian with our cut tree, and that creates a matrix, assuming Brownian motion, of course. And then you can run a GLS, which is a general least squares model, assuming Brownian motion. And so here you can see it's in the NLME package, and it's a GLS. And we're going to be looking at how the length of a note sung by a barbet is a function of the altitude where you might find that barbet. And we're going to be using the correlation matrix of the Brownian motion. So you just use correlation equals BM. And here's your summary. So you can see that the altitude that the birds are found at actually do make a difference for the length of their notes and when they're singing. But maybe we don't want to assume Brownian motion. There's lots of different models for how we assume evolution might occur. And so what if we want to assume a Pagel's lambda model? And this model stretches tip branches relative to internal branches. And here you can see that we can run the same GLS model as we did before, but we can specify our correlation function slightly differently with the core Pagel, again with our cut tree. And this formulation looks very similar to how we were adding a correlation structure with an AR1 model or an ARMA model when we had autocorrelation, where we had our model, we just wrote correlation equals, and then we specify the type. And so here we're just saying core Pagel. But you can also do this with mixed effects models. So if you have that correlation matrix, the Brownian motion matrix, you can take your mixed effects model where you can look at the function of the length of a note that a barbet sings is a function of its altitude. And the random effect could be habitat here. For example, birds live in different habitats, and you want to take that into account. And then your correlation would then be this phylogenetic tree, assuming Brownian motion. And here you can see that actually when we do this, we get quite a significant result. And so with that, please complete quiz 11.3 on Canvas. And this is the last lecture for this week and for the course.